Hello, this is Mr. Smith with Reading Quiz 13 on logistic equations, and we've seen regular exponential growth up until now. And now we take a look at what happens if we apply a limiting factor to our differential equation. As you know, not everything grows exponentially, and so we need to make sure that we account for any differences we might have with carrying capacity, etc. So, just a little reminder, what is a logistic equation? It's an equation of the form P is equal to m over 1 plus 1 over a times e to the negative mkt. That looks really complicated. We saw very similar sort of things in pre-calculus, but a has a little bit to do with the initial population, p sub 0 over n minus p sub 0. In this case, m is what we call the carrying capacity of our population. And the derivative that corresponds to this type of equation is dp dt is equal to k times p times n minus p. The n minus p portion is called the limiting factor. It helps limit the population. And p, of course, is our population, and k, is our growth rate. And as I just mentioned, m is our carrying capacity. P sub 0 up here, where I describe what a is our initial population. Unlike exponential growth, in which case dp dt is equal to k times p, logistic growth models include what's called a limiting factor, and we'll see why that's important on the next slide. So some facts about logistic equations. Using integration by partial fractions, which we'll see, we'll be able to show that this differential equation will transform into our logistic equation we saw in pre-calculus. The other key thing is the differential equation produces growth rates close to 0 at p is equal to 0 and p is equal to m. So taking it back a step, if you notice the differential equation dp dt is equal to kp times m minus p, there are two situations where our derivative would be equal to 0 here. That would be if p is equal to 0 or if m is equal to p. In other words, if our carrying capacity equals our population. So that makes sense. We level off and have no growth rate at the moment we're starting and at the moment when we level off to our carrying capacity. Growth rate is maximized, as you saw in the lab, when the population reaches half of its carrying capacity. At that point, we reach an inflection point of our logistic equation, and we start to slow down our growth rate. The limit as t goes to infinity of p of t, or our population, depends on where you start, but we're going to level off to m if our population is non-negative. So that's an important thing to keep in mind. And one way that you'll see these equations sometimes is that dp dt is equal to k times p times 1 minus p over m. This is really kind of the same idea. The only thing that gets adjusted is our k, our growth rate. And in this case, our carrying capacity is still m, no matter what we're seeing it. And the way to notice that is that, just as I said before, the differential equation produces growth rates close to 0 at p is equal to 0, which this one still does, and also at p is equal to m, which this one still does as well. So these are the same equations. Example 1, this is adapted from a book I have by the author Finney. A 2,000-gallon tank can support a maximum number of guppies. 6 guppies are introduced into the tank. Assume that the rate of growth of the population is dp dt is equal to 0.0015 p times 150 minus p, where t is the time in weeks. Part A, what is the carrying capacity of the population? And as we just mentioned, the growth rate is equal to 0 whenever our population is 0, and also when our population equals our carrying capacity. So from this equation, we can see pretty easily that our carrying capacity would have to be 150 in order for that limiting factor to be equal to 0. Part B, what population is the rate of growth the fastest, and what is that rate? The maximum occurs when we reach half of our carrying capacity, which would be p is equal to 75. And then what we can do is we can plug in our 75 for p to find that our rate at that moment is 8.438 guppies per week. Guppies per week because t is measured in weeks. Part C, what is the limit as t goes to infinity of p of t? And then what is the limit as t goes to infinity of the rate dp dt? As time goes on, our positive population will level off towards the carrying capacity, as we mentioned before, or 150 guppies. And then at that point, the limit of our rate will also be 0 because we're leveling off to our carrying capacity. So it's important to make a distinction between these two limits here. A 2,000-gallon tank can support a maximum number of guppies. Same sort of thing as before. Find a formula for the guppy population in terms of T. You'll notice that my writing is pretty small because I'll go through every step of the integration by partial fractions that we need to do to solve for the population. This is a separable differential equation that can be solved using integration by partial fractions. So there's the original. We are going to divide by P and by 150 minus P to get it onto the left side, similar to the way we did with differential equations with separation of variables. I'm going to leave the point 0015 on the right side of the equation. Using partial fraction decomposition, which I won't get into here, we find out that dp over p times 150 minus p is just 1 over 150 over p plus 1 over 150 over 150 minus p. And that's using the techniques we did when we did partial fractions. Now I rewrite this as 1 over 150 times the integral of dp over p plus 1 over 150 times of the integral dp over 150 minus p, integrating both sides in this case. We get 1 over 150 times natural log absolute value of p minus 1 over 150 natural log of 150 minus p. That minus comes from the fact that we have a negative p inside of our integrand, and so we need to account for that because of the chain rule. And then we integrate the right side and get 0.0015t plus c. I'm going to combine using our log laws. This is very helpful here. And I'm also going to move the 150 over by multiplying both sides by 150 so that we can just deal with the natural log here. So we end up getting natural log of absolute value of p over 150 minus p is equal to 0.225t plus another constant, which we'll call c2. Here we're going to let k is equal to plus or minus e to the c2, which is something that we saw earlier last year when we did separable differential equations. We get p over 150 minus p is equal to k times e to the 0.225t. All right, this is our typical natural log sort of problem with differential equations. We plug in our initial condition, p of 0 is equal to 6. When we do so, I don't show all the work here, but you end up finding that k is equal to 1 over 24. So now what we do is we're going to move the 150 minus p over to the right side by cross multiplying. I'm going to distribute, and that way I distributed 150 times 1 over 24 times e to the 0.225t. That's the first part, minus p over 24 times e to the 0.225t. I'm going to group all my p terms together by moving the last factor on the right over to the left side. Right here, what I do to make things a little bit easier is I multiply both sides by 24. And then I factor out a p from both sides and divide. So we end up with p is equal to 150 times e to the 0.225t over 24 plus e to the 0.225t. And typically we write this by having our carrying capacity on our top, so this is easy to read. The way to get that is I divide by e to the 0.225t on the top and the bottom, and that allows me to get 1 plus 24 e to the negative 0.225t on the bottom. Example 2. This is from the Stewart book. The logistic equation dp dt is equal to 0.08p times 1 minus p over 1,000 describes the growth of the population, with p of 0 equal to 1,000 and t measured in years. Part A, find the carrying capacity of the population. Again, we're in a logistic differential equation form, and so we can find our carrying capacity pretty easily by looking at that limiting factor. M has to be 1,000 here in order for our limiting factor to be equal to 0 and have our derivative equal to 0 at our carrying capacity. Find the size of the population when it's growing the fastest. As I mentioned before, we're growing the fastest at half our carrying capacity, which in this case is when m is equal to 500. And then find the rate at which the population is growing when it is growing the fastest. And we can just plug in 500 into this, and we get a rate of 20 units per year. Example 3. One model for the spread of a rumor is that the rate of spread is proportional to the product of the fraction y of the population who have heard the rumor and the fraction who have not heard the rumor. Part A, one of the things that the AP exam asks you to do is write differential equations that model certain situations. So in this case, they asked us to write a differential equation that is satisfied by y. We say dy dt is equal to k times y, where k is our constant of proportionality. and y is the fraction of the population who have heard the rumor. We also need to account for the fraction who have not heard the rumor, and assuming that our proportion adds up to 1, then our limiting factor is then 1 minus y here. Part B, solve the differential equation. Just like before, we want to use partial fraction decomposition. We need to separate our variables, get all of our y's together, so we end up with dy over y times 1 minus y is equal to k dt. Some side work indicates that partial fractions gives us 1 over y plus 1 over 1 minus y. When we integrate both sides, we end up with natural log of y minus natural log of absolute value of 1 minus y with absolute value in the first part 2. The minus, again, comes from the fact that we have a negative y, and we need to account for that negative with the chain rule. We end up with natural log of absolute value y minus natural log of absolute value of 1 minus y is equal to kt plus c. Combined, just like on example 1, using our log laws, we're going to raise each side to the 1 minus y power. In doing so, we're going to raise each side to the e power, and we're going to get e to the negative kt, and m is going to represent plus or minus e to the c. And when we go through and we solve, we get y is equal to 1 over 1 plus m e to the negative kt. I believe I've got a little mistake there. This should be a positive kt right here. Sorry about that. A small town has 1,000 inhabitants. By 8 a.m., 80 people have heard a rumor. By noon, half the town has heard it. At what time will 90% of the population have heard the rumor? And using our formula from slide 2, or slide 1 rather, where y is equal to 1 over 1 plus m e to the negative kt, we can figure out what our m is by plugging in time equal to 0 is 8 a.m. And we know our proportion is 80 people out of 1,000, which is 0.08. Solving for m, we get 11.5. We also know at time 4 that we know half the people has heard the rumor. So at time 4, that would be noon. So we plug in 0.5 for our proportion, and we plug in our time 4, and that'll allow us to solve for k equal to 0.611. Plugging that in, we can then find that 90% of the population hears the rumor at about time t equal to 7.593, which is about 3:36 p.m. What amazing precision.